In the family of logic devices, next we will look into another very prominent structure that you will find in today's digital design field, which is known as field programmable gate array, or in short FPGA. So, this, as the name suggests, so it is field programmable, means the programming of the device can be done at the customer end. So, just like we can program a PROM, that is programmable read only memory, or say PLA. So, here also we can do the programming and the programming can be done at your ends, that you can just buy the device and connect some you have to have some sort of burner, and through that burner, so the control program can be loaded onto this FPGA chip, and then the FPGA chip will be customized to your particular application. So, it does not need detailed semiconductor manufacturing phases. So, the last phase, that is the final connection of the module, so that can be done at the customer point. So, that drastically reduces the design turnaround time. So, that is why it has become very popular, and also it is in many cases, so it is reprogrammable. So, you can change the design. So, if there is an error, so you can very easily correct it, or if there is some modification or upgradation of the design, so those things can be carried out very easily. So, if we look into the evolution of this implementation technologies, so it started with logic gates in 1950s and 60s. Then there was regular structures for two level logic gate 1960s 70s. So, two level logic means so you have got an AND level and an OR level. So, this to a PLA type of structures. Then from there it evolved to more complex programmable devices, which are known as PLDs, programmable logic devices, or CPLDs, complex programmable logic devices. That was 1970s and 18s. Then came the programmable gate array. So, programmable gate arrays means you have got an array of gates of similar type, and then you can just connect them in some fashion to get the overall functionality implemented. So, in programmable gate array, so density is high enough to permit entirely new class of application. For example, prototyping, emulation, acceleration. So, entire design, entire hardware design you can prototype onto these programmable gate arrays, and you can get the thing done. So, you can have a basic idea about whether your design is going to work or not by doing a proper simulation or emulation of the system. So, if as you go from this logic gates toward this lower side programmable gate arrays, so these higher levels of integration can be seen. So, more and more number of gates can be clapped onto one device. So, you can, as a result, you can implement more complex designs. So, if we just look into the gate array, so that was gate array. So, it was so this is gate array technology. So, it came from IBM in 1970s. So, the overall structure is similar to this. So, we have got a simple logic gates. So, like this. So, these are logic gates implemented in some layer, and then there are some interconnects running in between. So, this interconnect, so they are running between the layers. So, between the you can say between the rows of these logic elements, and then these logic elements, they are implementing some function. So, if you want to establish a connection from here to here, say for example, so you have to make a connection like this, and then at this point you have to make a connection like this. So, what I mean is so maybe output of this module has to be fed to the input of this module. So, you can use this interconnect to do the connection like this. So, this way these gate arrays can be combined through these interconnects to implement complex logic. Apart from that, there are some IO blocks. So, from normally this IO comes from the outside world. So, for driving these logic gates, you need some inputs, and those inputs are given through this input block, and outputs are taken from the output block. And as so to have protection against over voltage, or to have a higher drive current, etc. These I/O blocks are designed in a much are designed in such a fashion that they are capable of driving more load, or they are capable of withstanding noise margins sufficiently. So, that way these I/O blocks are designed. So, they are special blocks at the periphery of for external connections. Then we can add wires to make connections. So, as I was showing there, so you can have some extra wire connected, and between these. So, these wires, these vertical wires are not shown here, but so there are connections from this, and all those connections are programmable. So, if you need to establish a connection, then you need to burn out some of the points, and as a result the connections will get established, and the output of one block will be connected to input of another block. So, that way complex logic can be implemented. So, as a result, so this is done when the chip is fabricated. So, we can, or the mask, it is called mask programmable, because we can put a mask for this type of connection, and then we can do the connection, or it may be. So, this is mask programmable because this is not even not yet in the customer side. So, this has to be done, the final stage of connection has to be done at the fabrication house itself, but before the design has arrived to the fabrication house. So, the remaining part is fabricated. So, only when this when the final connection when the design comes and the connections are determined. So, the final metallization stage is carried out, and it establishes the connection between the logic elements. So, it can be used for constructing any circuit. Next, we will be looking into field programmable gate array. So, in field programmable gate array, so it is otherwise similar. So, we have got logic blocks to implement combinational and sequential logic. So, there are some logic gates and there are some flip flops which are part of this logic block, that can be used for implementing combinational and sequential logic. Then there are interconnects running both horizontally and vertically. So, this the gray region, so they are for running interconnect, and you can have some switches at these junction points. So, these junction points are not shown explicitly. So, you can have some switch here, and that switch will determine the connection from between the horizontal and vertical lines. So, we have got interconnects, that is wires to connect inputs and output logic blocks, and the I/O blocks for the input output operation. So, these are special logic blocks at periphery of device for external connection. So, the questions that we have is, first of all, how to make these logic blocks programmable. So, I said that you can there may be some sort of logic elements there, but those logic elements may be programmed to have different combinational and sequential function implemented. So, how to make these logic blocks programmable? How to connect the wires, like as I was telling that I need to connect the output of this logic block to the input of this logic block. So, how do we establish the connection? And naturally, when we say it is field programmable, so this field means it has to be done after the chip has been given to the customer. So, at the customer side we should be able to do this programming part. So, the design never goes to the fabrication house. So, it is always the design is with the customer only, and then getting one FPGA chip, the customer should be able to program it, so that it gives the proper function. So, there are two types of logic devices that comes under this field programmable capability. One is known as CPLD, or complex programmable logic device, and another is called FPGA, or field programmable gate array. Out of these two, CPLD has a somewhat restrictive structure consisting of one or more programmable sum of products logic array feeding a relatively small number of clocked registers. So, in CPLD the basic structure will be something like a two level structure. So, sum of product type of logic array will be there, and or planes will be there, and they will feed some number of clocked flip flops. So, and overall CPLD capacity wise it is less, capacity is less compared to FPGA. So, as a result the CPLD it has got less flexibility with the advantage of more predictable timing delays and a higher logic to interconnect ratio. So, it is less flexible, but at the same time this timing delays that will occur is predictable. So, even if this logic is implemented in the programmable part, so the distance between those points or the lengths of the wires are predictable. So, as a result the timing delays are predictable, and higher logic to interconnect ratio means you have there are more number of logic elements compared to interconnect. So, it is likely that we can push in more number of logic gates onto the CPLD structure. On the other hand, these FPGA architectures, they are dominated by interconnect. So, they have got large number of interconnects in them, so that you can establish connection between logic elements very easily, logic elements and flip flops, which is not the case for CPLD. So, this availability of interconnect, so this makes them far more flexible in terms of the range of designs that are practical for implementation within them, but also for far more complex to design for. So, that gives us the flexibility that you can have very wide range of designs implemented there, but at the same time it makes it very complex also. So, you normally nobody does an FPGA based design manually. So, normally the CAD tools are used for doing the design. In practice, the distinction between FPGAs and CPLDs is often one of size, as FPGAs are usually much higher in terms of resources than CPLDs. So, the total amount of logic elements that we have in FPGA, total amount of interconnects that we have in FPGA, so they are much more compared to CPLDs. So, these FPGAs they are going to be much larger than CPLDs. Typically, only FPGAs contain more advanced embedded functions such as adders, multipliers, memory and other hardened functions. So, what I mean is that if you look into advanced FPGAs now, so you will find that there are built-in adder available, built-in multipliers available, and memories are also available, because if you are trying to make a design, so if you are trying to make a system, so normally what you will need is, apart from this logic element processing, you will require some amount of memory, and many a times we need this addition, subtraction, multiplication, division type of operations. So, they if we have built-in modules for that, then the implementation will be much more efficient compared to the customer making the implementation by himself. So, that way FPGAs, advanced FPGAs, they will contain this adder, multiplier, memory and other functions which are not available in case of CPLDs. Another common distinction is that CPLDs contain embedded flash to store their configuration, while FPGAs usually but not always require an external flash. So, CPLD devices, they have got a flash memory within them. So, as a result, even if this power is even if it is switched off, then the flash will contain the configuration program. So, when it is turned on, so the CPLD functionality remains same. Whereas, in case of FPGAs, in many FPGAs you will find that it will require an external flash. So, whenever you power on the FPGA chip or you give a reset, so it will load the program from the external memory, and then it will external flash, and then it will into an internal RAM, and then it will start operating in that fashion. So, the point is that this embedded flash in CPLD, that is good, because you do not need this external flash, but at the same time it stops you from getting the reprogrammability. So, if I have got an external flash for this programming purpose, so I can just change the configuration program in the external flash, and we can get a new functionality realized by the same FPGA chip, which is not true for CPLDs. So, if we look into this programmability feature of FPGAs, so user programmability of CPLDs and FPGAs is achieved via user programmable switch technologies. So, both CPLD and FPGA, they use some sort of switch technology. For CPLDs, we have got floating gate transistors like EEPROM or EEPROM. So, floating gate transistors, you know that it is these are transistors. So, if you apply control voltage, then the gate will appear. So, as a result, the communication, the device will be turned on, and if you remove the voltage, then this or if you apply some negative voltage or to remove that gate terminal. So, basically this is a transistor. So, this is so you know that this is a transistor. Now, in this is a normal gate. Now, there is another gate in case of CPLD and this the floating gate thing. So, you have got another transistor, another gate that will appear. So, when you apply the voltage, this additional gate appears, as a result the device gets turned on. Even if you remove this voltage now, this gate will remain. So, as the CPLD or FPGA using this floating gate technology, so it will remain programmed in the same status. Now, to remove this floating gate, you have to apply some other voltage, and then this will be going out. So, these are CPLDs, they use normally this floating gate philosophy of this like EEPROM or EEPROM. FPGAs, they normally use static RAM or anti-fuse technology. Of course, there are FPGAs that use floating gate as well, but many of them use this static RAM or this anti-fuse technology. So, properties of the switches such as size, on resistance and capacitance dictate trade-off between the trade-offs in the architecture. So, these switches, they are coming as extra. So, we need them for programming the device, but they do not participate in forming the logic part of the design. So, as a result, they are overheads, you can say. So, their size, on resistance size will determine the what is the amount of logic that you can put there. On resistance will determine the delay in the communication. So, on resistance and capacitance, they will dictate the delay that you will have in the design. In SRAM based FPGAs, there is an SRAM bit corresponding to each of the programmable points within the device. So, device has got many programmable points, like between two, whenever we have got two interconnects, whether those two interconnects are connected to each other or not. So, that is controlled by one SRAM bit. Similarly, so the programmable device, so wherever you can think about programmability, so it is implemented by one SRAM bit. So, there are large number of SRAM bits, and that actually constitutes the configuration program. And when this FPGA, SRAM based FPGAs, they are switched on, so we get this this configuration program is loaded onto the FPGA. So, that all those programmable points are now programmed to have proper values, and then the chip behaves accordingly. So, we will look into this SRAM programming techniques slightly later. Now, so this is the thing, that when the device is powered on or reset, SRAM based FPGA, so it reads configuration program from an off chip memory and loads it into on chip SRAM. So, the chip, the FPGA chip will have got an SRAM which will have the configuration program. So, when the chip is switched on or reset, it is the configuration program will be loaded from off chip memory to the SRAM. The configuration program defines the logic function realized by individual logic blocks and interconnections. So, that will be determining the logic that is implemented by the logic blocks that we have and the interconnection. So, that will determine the overall functionality of the FPGA chip. Devices using SRAM based switching can be reprogrammed easily by just changing the configuration program. So, that is very good, because if I normally what happens is that when you are in the early stage of your design, so there will be design bugs. So, if you go for directly chip fabrication, then there is a possibility that many of those bugs are not detected at the time of design. So, what we can do, we can put this design onto an FPGA chip and we can check for the functionality, whether the chip is working properly or not. If we find some bug there, then nothing is lost, because I can just change the configuration program. So, I can correct my design. As a result, it gives a new configuration program, and that new configuration program can be loaded onto the again that SRAM based configuration memory, and that gives us the corrected chip. And also, if you are going for some upgradation, like you have got some functionality, so you want to add a new function, then also these FPGAs are going to be helpful, because all that you need is to change the configuration program. Now, FPGAs belonging to Xilinx, Plassey, Algotronics, Concurrent Logic, Toshiba, so they all use this SRAM based FPGA, SRAM based programming technologies. In fact, there are a large number of vendors for these FPGAs, and these are some of them. Out of these, Xilinx is the most popular because of its capabilities, as we will see later. others are also there. So, they are also used in many applications. SRAM provides fast reprogrammability at the cost of large area. So, as I said, the reprogrammability becomes very easy, because you can very easily change the configuration program. However, the area occupied is more, because each SRAM bit will require 5 transistors. Okay. So, that way if I have got say 10,000 programmable points, so there will be 50,000 transistors just needed for making the configuration memory. So, that makes it very costly. Anyway, so that is a trade off. So, if you are asking for flexibility, we have to pay for that, and this is the payment that we have to do, the amount of extra space that is needed, extra area that is needed for the FPGA. So, this diagram, it shows how this SRAM can control the switching. So, these are suppose some logic blocks within the FPGA, and we want to establish a connection. So, output of this logic block should feed the input of this logic block. So, how to do that? So, this interconnect, okay. So, this interconnect comes to this is a switch box, okay. So, this is a switch box. So, it has got this line and this line as two lines there, and there is a programmable transistor here. So, this SRAM bit is going to control this transistor. So, if this bit is equal to 1, in that case this transistor is on, as a result a connection is established between this line and this line. So, with this the signal that is available, that is given here, will be available at this point. Similarly, if this point is equal to 1, this SRAM bit is equal to 1. So, connection is established between this line and this line, this transistor is turned on and these two lines are now shorted. So, as a result the output of this logic block will come to the input of this logic block. So, that will happen. And similarly, whatever, like here you see that there are 4 lines coming as input, 4 lines going there out as output, and similarly 4 more lines will come, 4 more columns will come vertically and go out vertically. So, between all these points, so we have got this type of programmable transistors, and by putting the proper SRAM bit equal to 1, so we can establish the connection. So, if we do not want the connection, then the SRAM bit is 0. If we want the connection, then the SRAM bit is equal to 1. So, this way we can use this controlled SRAM to control the switching. Major problem with this SRAM based control is that the area that you need. Okay. So, another type of programming technology that is popular with FPGAs is known as anti-fuse based programming. So, anti-fuses they are originally open circuit. So, it is like this. So, conceptually you can view it like this. So, this is these are the 2 points, and in between we have got a anti-fuse. So, this anti-fuse on this is open circuit, normally it is open circuit, and that as a result the resistance between these 2 points is very high. Resistance between these 2 points is very high. Now, if we apply a programming voltage, so 11 to 20 volt across the terminals, then as if so this connection gets shorted. Okay. So, this resistance becomes very low, and that establishes an electric connection. And now, even if you withdraw the voltage, the programming voltage, the connection remains. Okay. So, that is how this is going to be useful. So, wherever you need the connections or programming, so we have to apply proper voltage across the terminals, so that the resistance becomes low, the on resistance becomes low. So, we have the connection gets established. So, anti-fuses advantage that we have with anti-fuse is that they can be made very small. Okay. So, they can be made very small using some modified CMOS technology, thus offering very high device density compared to SRAM. So, SRAM is 6 transistor cell I said. So, compared to that these anti-fuses can be made very small. So, that is why you can accommodate large number of anti-fuses within small chip area. So, that is why it is very popular. But the difficulty with anti-fuse is that once it is programmed, they cannot be reused. So, it is for one time use only. So, this is this cannot be reused. So, the device is one time programmable. So, we do not get the flexibility that I can use the same chip again and again, and the other advantage that we had, like say if there is a design error So, we can we can correct the error and use the same FPGA chip for corrected design. So, that is not possible for anti-fuse based FPGAs, but still they are popular because of their low cost and this size of the anti-fuse being small. So, this anti-fuse structure, so they are commonly known as splice, programmable low impedance circuit element. So, and this splice, it uses as far as manufacturing is concerned, it uses polysilicon and N plus diffusions as conductor and ONO, that is silicon dioxide, silicon nitride, silicon dioxide as an insulator. So, the advantages that you have that include a small size, little more than the cross section of 2 metal wires. So, as that is why it is size is pretty small, and it has got low series resistance. So, the resistance of this anti-fuse is very small when it is programmed. At disadvantage, so large size of programming transistors. So, this 11 to 12 20 volt that I said has to be applied. So, that volt has to be generated across the across those programming elements. So, programming transistors become large and need of isolation transistor. So, normally that 11 to 12 20 volts, so if it comes across some other circuit element, that circuit element may get damaged. So, they need to be applied specifically to these programming terminals. So, that way we need some isolation transistors, and it is one time programmable. So, that I have already said that it is, you can program it only once. So, FPGAs from Actel, QuickLogic, Crosspoint, they support these anti-fuses. So, these are some of these standard FPGAs that we have that support this anti-fuse based programming. So, this is the anti-fuse structure. So, symbolically it is represented like this. So, whereas the structurally, so you have got this oxide layer, then there is a there is a N plus diffusion, and this is another oxide layer, and we have got this polysilicon layer. So, this is the dielectric that we have. So, this dielectric, if it is if we apply a potential, then this dielectric will break, it will establish a connection between this polysilicon and this N plus diffusion. So, that is how the connection gets established and we get this anti-fuse based structure. Other programming technology that we have is the floating gate technology. So, FPGAs from Altera, PlusLogic, AMD, etc., they use this floating gate programming technology. So, this Altera and PlusLogic, they use ultraviolet erasable EEPROM. So, and AMD uses electrically erasable EEPROM. So, we know that there is EEPROM and EEPROM. So, this Altera and PlusLogic, they use EEPROM technology, and this AMD uses EEPROM technology. So, as I said that it contains a control gate and a floating gate. A transistor can be disabled by applying a high voltage between the control gate and drain. This injects charge on the floating gate, increasing the threshold voltage of the transistor, and it will get disabled. So, threshold voltage of the transistor, if it is increased, means to apply, to turn on the transistor. So, you have to apply more voltage. So, this is the diagram. So, if you apply some voltage here, then this floating gate appears. So, as a result, the threshold voltage of this transistor goes up. So, transistor becomes normally off sort of thing. Whereas, if this is not there, then the threshold voltage is low. So, then this you have got this transistor on. So, this floating gate that we can insert, and the charge can be removed by exposing the floating gate to ultraviolet light or by erasing it electrically. It provides reprogrammability, and unlike SRAM, no external memory is needed for to program the chip on power up. So, this is reprogrammable because you can remove that floating gate by applying either ultraviolet light or this high voltage, but unlike SRAM, so it does not need this off chip this reprogrammable off chip memory for to hold the control program. This EEPROM technology, it requires additional processing steps, of course, the high on resistance and high static power consumption due to pull up resistor. So, this is the problem with EEPROM technology. So, that is there with the floating gate based this FPGAs. So, this is the floating gate programming I said. So, if you want to apply a particular if you apply a voltage, then this gate will appear here, and as a result this will be, this threshold voltage will increase, whereas if you do not apply the voltage, the threshold, this floating gate will not be there. So, threshold voltage will be low. So, the transistor will be treated as on. So, that way we can establish connection or not.